When using the binomial formula, I always like to change the original problem to x plus y. Copy the exponent of the original problem, in this case it's a 5. And because I'm going to use an exponent that's relatively low, you can use Pascal's triangle for the coefficients. So Pascal's triangle starts with the triangle of ones. The ones continue on the outside. If you add those two numbers together and place it between them below it, that will continue the pattern. Ones down the outside, add these two numbers together, and place it between it, below it. We need to get to the row where the second digit is a 5, because the original exponent is a 5. So this is the row we are going to use for this particular problem. These are the coefficients for the 6 terms in the expansion of this problem. The number of terms is always one more than the original exponent. So, starting with 5 x's, the x's decrease by 1 each time, so there would be 4, then 3, then 2, and then 1. The y pattern, it starts with no y's, and then it has 1 and increases by 1 each time. Until you get to the same exponent as the original problem. Now, one pattern that is important to recognize, the exponent in each of these groupings adds to 5. It adds to the original exponent. So I'm going to go back and insert my plus symbols and copy the coefficients from this row. It starts with 1, it ends with 1, that's these particular ones. The second number is a 5, the second to last number is a 5. The middle two here in this case are 10s. So this would be the expansion of x plus y to the 5th power. Now I substitute all the x's with 3p. When you substitute, make sure you use parentheses. So for example, the first x becomes 3p to the 5th. The 5th goes with the 3 and the p. So we need to keep that in mind. 3 to the 5th and p to the 5th is what I'll write down below. 243 p to the 5th. If we continue to substitute all the x's with 3p and the y's with negative q, we'll have an expansion that we'll need to tidy up. So, sticking 3p for that x, raise it to the 4th power, insert our y, which is now negative q, we end up with that expression. 3 to the 4th times 5 times negative 1 is the next term, which is negative 405. We still have p to the 4th, and we still have q. Next, 10, 3p to the 3rd, negative q squared. That's this term right here. 3 to the 3rd is 27. 27 times 10 is 270. And negative 1 squared is positive 1. So this will become positive 270. I still have p cubed and q squared. 4th term, 10, 3p squared and negative q to the 3rd. 9 times 10 is 90. Negative 1 cubed is negative 1. So I have negative 1 times 90, which is negative 90. P squared q cubed. 3p here will generate a 15 plus 15 p q4. And the last term, which is going to get squishy, I have to stick negative q here and raise it to the 5th power. Negative 1 to the 5th power is negative 1, so this will end with minus q to the 5th. So that is our complete expansion for this problem. So I'm going to throw up example number 2. Here is example number 2. You're going to go ahead and press pause. Be sure and write out your Pascal triangle to figure out the coefficients for the 4. Press pause now and I'll reveal the answer. Okay. The answer to number 2 is here. I don't have Pascal's triangle drawn. I'll redraw it for you. So you'll see the coefficients of this row used 1, 4, 6, 4, 1. Continue the pattern with the variables. X is decreased by 1 each time, the y is increased by 1 each time, and then substitute. All x's get substituted with 2m, all y's get substituted with negative 2n here. Simplify the coefficients as much as possible. Alright, here is example number 3. Okay, g minus 2q to the 6th power. You need to press pause right now and work on this problem. And here is the solution to problem number 3. Terrific.